Welcome to the pod-key summary of Serpin. Today's thread is serpins, a family of proteins that do a lot more than their slightly niche name suggests. They can trap dangerous enzymes in a one-and-done shutdown move, flip between different shapes to control when they're active, and in some cases get repurposed for hormone transport, cell signaling, or even viral immune evasion. They're also a great example of biology being both elegant and a little fragile, because the same shape-shifting trick that makes serpins useful can also make them disease-prone. The most famous thing serpins do is act as what researchers call suicide inhibitors, which is dramatic wording, but honestly it fits. A regular protease inhibitor might just sit in an enzyme's active site and block it for a while. A serpin does something more irreversible. It presents an exposed reactive center loop. The target protease cuts that loop, and then the serpin snaps into a new shape so fast that it drags the protease along with it. That move distorts the protease into an inactive form while it's still covalently attached, and the complex can stay stuck together for days or even weeks. So each serpin molecule gets one shot. It disables one target protease permanently, and then that serpin is done. What's especially neat is that this basic mechanism can shut down both serine proteases and cysteine proteases, even though those enzyme classes use different chemistry at their catalytic core. Serpins only make sense if you think of them as shape-shifting proteins rather than rigid little locks waiting for matching keys. They're metastable, which means they sit in a stressed, ready state and can relax into a different conformation when the moment is right. That reactive loop can be fully exposed or partly tucked into a central beta sheet, and that shifting changes how available the serpin is for doing its job. This is where regulation gets clever. Allosteric cofactors can tip the balance toward the active form. A classic example is antithrombin. Heparin binds to it, helps expose an important arginine residue that was otherwise hidden, and also helps bring antithrombin together with clotting proteases like thrombin or factor XA. That basic insight didn't just stay in a textbook. It led to fondaparinux, a synthetic heparin pentasaccharide used as an anticoagulant. Once you see serpins as proteins built around controlled shape change, a lot of their odd-side careers start to make sense. Some of them can slip into an inactive latent state all by themselves, without even being cut. PAI1 is a good example. It stays active when it's bound to vitronectin, but otherwise it tends to auto-inactivate, which is a pretty tidy built-in timer. Antithrombin can also undergo latent conversion, adding yet another layer of control to coagulation. And some serpins have been repurposed away from enzyme inhibition altogether. Thyroxine-binding globulin and transcortin bind hormones tightly in their native state, then release them after cleavage pushes them into that relaxed conformation. In other cases, a cleaved serpin protease complex gets recognized by a receptor, so what started as protease inhibition turns into a cell signaling event. The flip side of all this beautiful flexibility is that serpins are unusually vulnerable to going wrong. If a mutation makes a serpin change shape too early, before it has trapped a protease, you end up with an inactive inhibitor that can't protect anything. One striking case is the antitrypsin Pittsburgh mutation, called M358R, which changes alpha-1 antitrypsin's target preference from tissue elastase to thrombin and causes a severe bleeding disorder. Serpins can also misfold into polymers, basically linked-up chains of inactive molecules with their reactive loops trapped in the wrong arrangement. These can appear as domain-swap dimers, trimers, and larger aggregates. That causes a double problem. You lose the active inhibitor in circulation, and at the same time, the aggregates can build up inside the endoplasmic reticulum, damage cells, and eventually contribute to organ failure. Alpha-1 antitrypsin deficiency is the clearest example of this two-sided damage. On one side, not enough active inhibitor means elastase in the lungs goes too far, chewing through tissue and contributing to emphysema. On the other side, polymer accumulation inside liver cells can lead to cirrhosis. Other serpin failures show up in very different systems. Antithrombin deficiency raises the risk of thrombosis, C1 inhibitor deficiency causes hereditary angioedema, and neuroserpin polymerization causes a rare dementia called familial encephalopathy with neuroserpin inclusion bodies. Therapy reflects that variety. There's intravenous plasma-derived antitrypsin augmentation, lung or liver transplantation in severe cases, gene correction work in induced pluripotent stem cells, and efforts to design small molecules that stop polymerization before it starts. The broader evolutionary story is maybe the most charming part of this whole family. More than 1,000 serpins have been identified across animals, plants, fungi, bacteria, archaea, and even some viruses, including 36 in humans. So despite the name, the serpinfold is not just one trick repeated forever. Some members are non-inhibitory from the start. Ovalbumin is likely an egg white storage protein. The hormone-binding globulins carry thyroxine or cortisol, and HSP47 is a collagen-folding chaperone that's essential for development. Viruses have also borrowed the fold for their own purposes, which feels very on-brand for viruses. Cowpox CRMA can suppress inflammatory and apoptotic pathways, and viral SERP1 can dampen toll-like receptor responses, and has even been investigated for transplantation and inflammatory disease applications. So the same underlying architecture can become an enzyme trap, a transporter, a chaperone, or an immune-modulating tool, depending on how evolution tweaks it. Serpins are one of those protein families that quietly connect biochemistry, medicine, and evolution all at once. They're powerful because they can change shape so dramatically, and that's also exactly why they can fail so dramatically. It's a pretty good reminder that in biology, flexibility is often the feature and the bug. This episode was generated by Podkey. Create your own at podkey.fm.